In the last lecture, we have introduced the concept of infinite series. So, the meaning of this infinite series, we have said that look at the nth partial sum. Now, if Sn as a sequence converges, then we say that this infinite series is a convergent series. Now, if this Sn diverges, then we say that this is not a convergent series. In other words, this is a divergent series. So, we have seen some particular series which are convergent and some particular series which are divergent. So, now what are the necessary condition for a series to be convergent? Now, look at this Sn, suppose is a convergent, then Sn is a convergent sequence. This will imply that the sequence Sn is bounded. Bounded means it is a bounded sequence. And also, if we look at S n plus 1 minus of S n, if we look at this, then this is going to be summation over n equal to 1 to n plus 1 a n minus summation n equal to 1 to n a n, which is equal to a n plus 1, right. So, now when S n is a convergent sequence, then we know that S n plus 1 minus of S n, this will go to 0 as n goes to infinity. So, in other words, suppose S n, if S n converges to S, then you can look at S n plus 1 minus of S n, this is lesser equal to S n plus 1 minus of S plus S n minus of S, both of them as n large become small. Therefore, S n plus 1 minus S n, that also goes to 0. So, from here we get that a n plus 1, this goes to 0, that means a n goes to 0. So, this we can put it as a theorem that if summation over n equal to 1 to infinity a n converges, then a n goes to 0 as n goes to infinity. The sequence a n that goes to 0 as n goes to infinity. So, this is a necessary condition for a convergent series. Now, if somebody gives us a series, then we see that whether a n converges to 0 or not. If it does not converge to 0, then obviously what we will say that the series is not a convergent series, this is a divergent series. For example, summation over n from 1 to infinity, this a n is equal to n, which does not go to 0. So, the series is divergent. So, that this is S n is also not bounded, therefore, this series is going to be divergent in either of the way. So, now if you look at summation over n equal to 1 to infinity sin of n, then as we know sin of n, this does not go to 0 as n goes to infinity. Therefore, this is a divergent series. However, not necessarily that if a n converges to 0, then it may not be true that summation over a n converges. This we have seen. Let a n is equal to 1 by n, then we have seen that summation over n equal to 1 to infinity 1 by n is a divergent series. So, this is a necessary condition. If the series a n converges, then this a n goes to 0, but if a n goes to 0, it may not be true that the series is convergent. This is what is an example of that. Okay, so, now this is an first, in order to see that whether the series converges or not, we will check that a n goes to 0 or not. If it does not go to 0, then the series is divergent. If it goes to 0, we cannot conclude anything. What we can say is that okay, there is a chance that the series may converge. So, that tells us that can we find some sufficient condition for the convergence of series. Okay. So, now one thing what one can easily see that, let us look at this thing. Let a n, all these a n's are non-negative for all n. Now, summation over a n converges if and only if the partial sum S n is bounded above. What we have seen is that if a n converges, then the partial sum definitely is going to be bounded, in particular bounded above. Now, for the converse of the thing, if the partial sum is bounded, is it necessarily mean that the series converges? If a n's are non-negative, then the answer is yes. So, one side of the proof already we have seen, if a n converges, S n is bounded. Now, S n is bounded above. Now, you look at, because a n's are non-negative, therefore, S n plus 1, this is equal to summation over n equal to 1 to n plus 1 a n, which is equal to summation n equal to 1 to n a n plus a n plus 1. Now, a n plus 1 is greater or equal to 0. Therefore, this is greater or equal to summation over n equal to 1 to n of a n, which is S n. So, therefore, the sequence S n is monotonically increasing. Now, if it is given to us that S n is bounded above, therefore, any monotonic sequence which is bounded above will be a convergent sequence. That is what we had seen in the convergence of sequence. If now S n bounded above will imply S n converges. So, series converges, Sn has to be bounded. Now, if the series consists of non-negative numbers, then Sn bounded will imply that the series is convergent. Okay. So, now one would like to have some test in which we can conclude that whether the series converges or not. So, the first one will say comparison So, now suppose G A n's and B n's are non-negative number for all n. Now, then summation B n converges will imply summation over A n converges. B summation n equal to 1 to infinity A n divergent, we have used the word the convergent and divergent. So, let us be consistent on this. This will imply summation over n equal to 1 to infinity B n divergent. You see, A and B, we need, if we can prove A, then B is automatic, because we want to show that this implies this B n divergent. If not, B n is convergent, then by A this will say that A n is convergent. So, if I want to show A implies B, or any statement P implies Q, not Q implies not P, will tell us that P implies Q. So, now first let us try to prove the first A part. Now, let me denote S n of A, n equal to 1 to n of A n, denote, and S n of B, let us denote it as n equal to 1 to n of B n. Now, in order to show that the series A n is convergent, what we need to show S n A is a convergent sequence. Now, look at S, what we have seen S n of A is lesser equal to S n plus 1 of A, because not A n's are non-negative. Here you are adding one more non-negative term. So, this is monotonically increasing. So, S n A monotonically increasing. Now, A n's are lesser equal to B n, therefore, this is lesser equal to S n plus 1 of B. Now, given to us that series B n converges, therefore, the nth partial sum S n B, it converges, which means it is a bounded sequence. So, this is lesser equal to m for some m greater or equal to 0. Now, this S and A, they are monotonically increasing sequence and which are bounded above, therefore, S n converges. So, S and A converges. this implies that the series A n this converges. So, this is the comparison test. Now, B is, as we have discussed earlier, is also true, because if this is B n is convergent, then A n is convergent, contrapositive statement. Now, let us do some example. So, let us look at summation over n equal to 1 to infinity 1 by n plus 1. Now, all these, look at these a n's here is 1 by n plus 1 square, n plus 1 square. These are all greater or equal to 0. Now, a n's are lesser equal to 1 by n into n plus 1, because n plus 1 is greater or equal to n. So, 1 by n plus 1 is lesser equal to 1 by n. What we have seen earlier by telescopic sum, what we have seen that summation over n equal to 1 to infinity 1 by n plus 1 convergent. Therefore, by comparison test, one by n plus 1 square summation over n equal to 1 to infinity convergent. So, therefore, we can conclude from here is that summation over n equal to 1 to infinity 1 by n square also convergent. Not only that, if I take p to be greater than or equal to 2, then 1 by n to the power p is lesser equal to 1 by n square, and all these are non-negative numbers. So, 1 by n to the power p convergent for p greater or equal to 2. That is what we have conclude. Now, let us look at summation over n equal to 1 by 1 to infinity 1 by square root of n. Now, definitely these are all non-negative numbers, square root of n we are taking to be non-negative number. Now, square root of n is lesser equal to n. So, this will imply that 1 by square root of n is greater or equal to 1 by n. So, if this is your a n, this is your b n, what we have seen is that summation over 1 by n diverges. Now, if that diverges, a n is going to diverge. So, there hence this is divergent. As you can see, there is nothing holy about square root of n. We can say that if p is less than 1, then n to the power p is lesser equal to n, because all these n's are greater or equal to 1. Therefore, summation over 1 by comparing with the series 1 by n, we conclude that this is divergent. So, now for the series, interestingly, 1 by n to the power p, we have if p lesser equal to 1 divergent, what we have seen p greater or equal to 2 convergent. Now, we need to answer what happened to this. So, this we will answer when 1 over n to the power p, p bigger than 1, whether it is convergent or divergent. Maybe we need to look for more tests to derive this. Just with the comparison, we are not able to derive 1 by n to the power p for p less than 2 greater than 1. Well, we will wait. As a matter of fact, this is going to be also convergent. Okay, so some more examples. Suppose if you look at summation over 1 by n factorial, n equal to 1 to infinity. Is this a convergent series or a divergent series? So, we need to compare with some non-negative series which is convergent or divergent to conclude that whether this series is a convergent series. So, compare this with summation over 1 by n square. What one can easily show that n square is lesser equal to n factorial for n greater or equal to 4. That is pretty easy to show. You can use induction or anything. Now, this is a convergent series 1 by n square. Therefore, this is also a convergent series. So, another important comparison test is limit comparison test. Suppose now remember that in all these comparison tests, what we are assuming that our a n and b n they are non-negative. Only when they are non-negative, then we can use the comparison test. Now, if it has a mixed sign positive, negative, then obviously we cannot conclude that this series is converged. We cannot compare two series. We apply comparison test provided both a n and b n they have the same sign. Okay. Now, suppose a n by b n this converges to L. Now, what we conclude that if L greater than 0, then both a n and series b n converges or diverges together. What does that mean? That means that if a n converges, then b n converges. If b n converges, then a n converges. If a n diverges, then b n diverges, b n diverges, then a n diverges. Second is that provided L is bigger than 0. Now, if L is equal to 0 and series B n converges, then series A n converges. We cannot say if L is equal to 0, then A n converges will imply B n converges, B n converges will imply A n converges. Then see if L is equal to infinity and diverges, imply A n diverges. Similarly, here I will put it as and. Okay, so the proof is not very hard. Let's have a quick look at the proof. So, L is greater than 0. Now, choose epsilon such that L minus of epsilon is greater than 0. Now, what we get that A n by B n, it converges to 0. So, there exists a n sub naught such that 0 is less than L minus of epsilon, which is less than A n by B n, less or equal to A n by B n, which is less than L minus of epsilon for all n greater or equal to n sub naught. So, therefore, as you can see that this is a positive number. So, you have A n is less or equal to L minus of epsilon of B n. Therefore, A n converges will imply B n converges. Will imply B n converges. Then from this inequality we get A n is less or equal to L minus of epsilon of B n. This will imply B n converges. So, therefore, A n and B n converges or diverges together. So, similarly, now if L equal to 0, this is the part A, part B L equal to 0 means A n by B n, this is 0 is less than epsilon. Therefore, what you get is that A n is less or equal to epsilon times B n. So, B n converges will imply A n converges. See, you can also see that B n diverges, because what you get is that A n by B n, this is greater than some alpha for all n greater or equal to n sub naught. Therefore, A n is greater than alpha times B n. So, what you get is that if B n diverges, then A n diverges. This is a sketch of the proof, but remember that in limit comparison test, what you have A n B n both are non-negative. If A n by B n, which is it goes to the limit L, and if L is positive, then both the series converges and diverges together. Now, if L is equal to 0, then if you have B n converges, then A n will converge. If it is infinity, then B n diverges will imply that A n is going to be a divergent series. We will see some examples based on this test in the next lecture. Thank you.